For this lesson, we want to identify all the minimums, maximums, and saddle points for this function of two variables. So this is a surface, and recall if we want to find a minimum or a maximum for a function of two variables, we think about a tangent plane. And the key idea of the tangent plane is that the partial derivative in the x direction, or the directional derivative in the x direction, is zero. The partial derivative in the y direction is zero. Similar to, in a function of one variable, a tangent line having a first derivative of zero representing a horizontal tangent for a possible minimum or a maximum. So we're going to need to identify the partial derivatives and set them equal to zero. So what do we get? F sub x is 4x cubed minus 4y. And f sub y is 4y cubed minus 4x. Now, setting them equal to zero, where do we get? In this first case, 4y cubed equals, 4y equals 4x cubed, y equals x cubed. Setting f sub y equal to zero, we get 4x equals 4y cubed, and we get x equals y cubed. So y equals x cubed and x equals y cubed. How do we solve that? Well, let me go ahead and do that with substitution. I will work off of the second version. X equals y cubed, but then I'm going to substitute for y equals x cubed. So x equals, we know y is x cubed, replace the y with x cubed. X equals x cubed cubed. So x equals x to the ninth. 0 equals x to the ninth minus x. 0 equals x times x to the eighth minus 1. And then we've got some factoring to do. 0 equals x times x to the fourth minus 1 times x to the fourth plus 1. 0 equals x times x squared minus 1, x squared plus 1, x to the fourth plus 1. 0 equals x minus 1, x plus 1, x squared plus 1, x to the fourth plus 1. So x squared plus 1 is never equal to 0. X to the fourth plus 1 is never equal to 0 in the real world. So that means x could be 0. X minus 1 could be 0. X plus 1 is 0. So the values I get x is 0. X is 1. X is negative 1. So those are the values for x when I solve that system of equations. And then what are the corresponding y values? So x could be 0, x could be 1, x could be negative 1. But what do we know? We know from this that y equals x cubed. Therefore, y is 0 cubed, which is 0. Y is 1 cubed is 1. Y is negative 1 cubed, which is negative 1. So I have 3 test points. We have 3 test points. They are 0, 0, 1, 1, and negative 1, negative 1. So those are places where we have horizontal tangent planes. So we've got to decide, are we going to have a minimum, a maximum, or a saddle point, or might the test fail? Those are the 3 conditions that we may have, and we determine that by looking at the second derivatives. So starting with the first derivative, we will next find f sub x, which is the partial derivative with respect to x of f sub x. So f sub x partial with respect to x of 4x cubed minus 4y. So what will that give me? F sub x, the partial of 4x cubed will be 12x squared. With respect to x of 4y is just 0. So we get that one for fxx. Now moving over to fyy is the partial with respect to y of f sub y. So fyy is the partial with respect to y of 4y cubed minus 4x. And very similarly, f sub yy is 12y squared. But now I've got to go ahead and get fxy and fyx, and they should be the same. fxy is the partial with respect to y of f sub x. So fxy is the partial with respect to y of 4x cubed minus 4y. The partial with respect to y of 4x cubed is 0, minus the partial with respect to y of 4y is 4. So we get f sub xy is negative 4. Now, f sub yx also should be negative 4, but I like to do that just to check to make sure I've done it correctly. F sub yx is the partial with respect to x of f sub y. F sub yx is the partial with respect to x of 4y cubed minus 4x. So f sub yx is again 0 minus 4. F sub yx is negative 4. So let's collect the information we have here to find our Hessian matrix and our D to determine if we have mins or maxes at our test points. Here's our collected information. We want to construct the Hessian matrix, which is built out of the second order partials, fxx, fxy, fyx, fyy. And what do we get? Fxx is 12x squared, fxy is negative 4, fyx is negative 4, and fyy is 12y squared. So D is the determinant of the Hessian matrix, which is fxx times fyy minus fxy squared. So what do we get for D? D is 12x squared times 12y squared minus negative 4 squared. D gives me 144 x squared y squared minus 16. Now, we have to apply D to all of my test points. Remember what they were? We had 3 test points. They were 0, 0, 1, 1, and negative 1, negative 1. We need to apply D to that as well as keep track of fxx. So let's collect all of that information to see what results. So there are our test points, 0, 0, 1, 1, negative 1, negative 1. There's our D, the determinant of the Hessian matrix. Plugging in 0, 0, we get 144 times 0 squared times 0 squared minus 16, which equals negative 16. And what do we recall? If D is less than 0, there is a saddle point at the test point. The test point is a saddle point. So this tells me right here that 0, 0 will be a saddle point. Now plugging in 1, 1, what do we get? We get 144 times 1 squared times 1 squared minus 16. 144 minus 16 is 128. So we have that, but we also need to know what fxx is. So what was fxx? We recall that fxx was 12x squared. So in this case, we would say fxx is 12 times 1 squared, which is 12. So what does that tell me? What's my rule there? So D is positive. If D is positive, and in this case, fxx is positive, then the test point is a local minimum. So this tells me 1, 1 is going to be a minimum. And we'll see the same thing is going to happen for -1, -1. We see that 144, -1 squared, -1 squared minus 16 equals 128. Fxx, again, is still 12x squared. So fxx is 12 times -1 squared, which is 12. So same rule, d is positive, it is 128. Fxx is positive, it is 12. Therefore, we are going to have a minimum. So my conclusion is 0, 0 should be a saddle point. One, 1 should be a local min. And -1, -1 should be a local min. So let's take a look at a graph to see if that is verified. So here we go. We have f of xy is x to the fourth plus y to the fourth minus 4xy plus 1. We believe that 0, 0 is a saddle point. But notice that's when x is 0, when y is 0. So in reality, what is f of 0, 0? F of 0, 0 is 1. So if we put that point on there, right, 0, 0, 1, you can see that green dot. We should be able to see the green dot. Indeed, that is a saddle point. Notice from this perspective, it appears to be a maximum. Whoops, that's spinning more than I want it to be. So coming up this way, it has appeared to be a maximum. And from the other way, it appears to be a minimum. Coming at it from this way, it appears to be a minimum. So a maximum from this perspective, a minimum coming down from the other perspective at the point 0, 0, 1. How about 1, 1? What is f of 1, 1? We believe it's going to be a local min. F of 1, 1 is -1. So let's put in the point 1, 1, -1. Choose the color, we can see a little better. So there we go. We can see this dot here. 1, 1, -1 certainly appears to be a local min. Similarly, how about f of -1, -1? That's -1 as well. So the point -1, -1, -1 should also be a local min, and it certainly appears to be the case. And we could even draw in the tangent plane for those local mins. So that would be at z equals -1. Do we see this tangent plane? So indeed, that tangent plane, we can see that f sub x partial in the x direction, partial in the y direction should be 0. Do you see the tangent plane at the saddle point? So where is that? So the saddle point was at 0, 0, 1. So if I draw in the tangent plane for the saddle point, that would be at z equals 1. A little harder to see, but indeed, the rate of change in the altitude in the x direction or the y direction at that saddle point is going to be 0. So indeed, we had a saddle point at 0, 0, or you could say 0, 0, 1 is the saddle point. We're saying 1, 1 is a local min. We could say f achieves a local min of -1 at the point 1, 1. So we could say f achieves a local min of -1 at 1, 1. Similarly, f achieves a local min of -1 at -1, -1.